Shows up. How come he shows up?
Yeah.
Must have been.
Yeah, I told him I'll give him a bribe if he shows up.
And your student also showing up, which is good. Ethan is already here. James is here.
Yep, let's see.
There's another faculty member. See?
That's cool.
Patrick's coming too.
Jingy is here.
Hey.
You might have a pretty good tour showing up, man. For a Friday. Oh, look, another faculty member.
Just say you know him.
I know.
Just say you all know me. That's good enough.
It will be a rainy day when so many faculty members show up for faculty
Yeah,
seminar.
Today's going to be the warmest day in the next 10 days.
The warm and rainy.
Warm and rainy.
All right, let's get started because it's already recording anyway. So people who want to watch it at home. It's a pleasure to introduce our seminar speaker today, Dr. Venkat Narayanaswamy, who is a faculty member in our department for about almost 10 years now. He got his PhD from UT Austin and then spent a year or two in Aachen, in Germany, before he came back and joined us here at NC State. As many of us know in the department, he's leading authority in high-speed flows, especially very well established reputation in diagnostics in high-speed flows. And also has been recently kind of the lead in charge of our work in hypersonics in the department. So he's going to share all the great stuff he's doing on campus. So go for it.
Okay. Thank you all for showing up. I really appreciate it. And so this talk is going to focus on the aspect of fluid structure interactions and material integration. Like all professors, I didn't do any of this. It's all done by my students. I'm just a marketing guy. So I'm just marketing whatever they did. And certainly want to acknowledge all the students for their hard work. Yeah, so there's a lot more to come, as you will see. So before I go into the talk, I just want to say that there has been a resurgence in the general area of hypersonics, and the resurgence is also accompanied by an age-old acknowledgement that pretty much every subsystem that you look in a hypersonic platform, there is a associated bottleneck with it. And these are some of the bottlenecks that I'm aware of, technology needs that I'm aware of, and this is certainly not an exhaustive list. These are some of the areas that I have been working in the past, so some of it will be shared to you. So to outline and summarize the key technologies that we have been working on in the domain of hypersonics which includes both on defense and civilian applications, mostly defense at this point, looking at long-range precision vehicles. Essentially, if you want to reach a target, you really want to reach a target not 20 kilometers away from the target. So, and that requires a lot of precision, a lot of control, a lot of guidance. So we do a lot of work to help with CNG, that is control, navigation, guidance models from our collaborators. The hypersonic environment, the flow is very, very hot. So, and there is very high shear, very hot. It's all prescription for a material failure. So we do a lot of work, at least in the recent past, on material integration, and this will be the core of this talk. And the end game, or the ultimate objective, is to develop tools that we can predict the predict the resulting thermal and mechanical loading and the onset of various nonlinear phenomena. And we also work in the domain of air breathing, propulsion, and combustion, where we work on developing fast screening computational tools, along with rapid prototyping of test articles and providing experimental data. We also work on counter-strike methods. So if you have an impending, if you want to deflect a vehicle that's coming at very high speeds, what do you do? So this is some of the recent accomplishment, but you'll see some of these through the talk. So what I want to do is I just want to give one slide overview of the key focus technologies that we have been working on. And at this point, I have to say that you will see that I've been getting a lot of help from a lot of people. So I will make sure to acknowledge pretty much almost everyone that I could remember at this point. But if you're not acknowledged, please, my apologies already. So first thing is on precision fires. Essentially, if you want to reach a target here, currently we have tools, and if the target is behind a barricade, this is obviously for military application. So we have tools that can plow through the barricade and reach the target with a smaller amount of strength. Or we have tools that can jump over the barricade and reach not the target, but somewhere away. So we have these two tools, but what we really want is we want to go over the barricade, make a very sharp turn, and reach the target. The problem with doing very sharp turns is that you have to deflect your control surfaces with aggressive angles. Once you do that, you create nonlinear flow phenomena that includes flow separation, and that redistributes the pressure loads, which redistributes the control forces, control moments. So this initiated an effort where we wanted to do very simple situation of you place a control surface onto a representative vehicle geometry. This is just a cylinder surface, and do very meticulous mapping of all the properties of that are relevant for modelers, which includes surface properties such as the pressure, off-surface properties such as the velocity. So here is the map of a surface pressure. Here is a scan of the off-body density that also shows you the shock structure. Here is the map of the 2D dilatation field, which is obtained from the velocity field. So I partnered with my former colleague Pramod Sabareddy, who did this really good DNS of this. It's a wall-resolved LES of this flow field. Not many people have such capabilities, and this is the first work where this level of fidelity was accomplished in this target. So the ultimate goal, like I said, is to create precision or make very sharp turns. And the point is that when you deflect control surfaces, you undergo flow separation. The question is, how do you mitigate or do away with flow separation, right? And when you do that, how do you do it in the most effective manner? When I say effective, the thing is, you want whatever control mechanism you apply or control actuator you apply, that should occupy the least amount of space. So in all these vehicles, acreage is the key. You cannot be putting in a big, fat control system. So they are looking for very miniaturized control. That's what they were looking for. And so what we did was we took this idea of vortex generators that has been there in other types of separation and control, and we adapted it. And these vortex generators needed to be machined in a very precise manner. And I want to acknowledge the help from Professor Bryant, who did all these precise manufacturing of the vortex generators for us. And this is the first, and as such, this is the only demonstration where we were able to control a relatively large separation from a control pin to literally zero separation. And if you see here, if you look at the pressure field, they are redistributed. So there are positive outcomes that came out of it, which also dovetailed into the mitigation of heat loading, unsteady loading. So those things also came out of it. But the big accomplishment that I wanted to highlight is that we could mitigate or completely annihilate the flow separation. The second top technology that we focused was SCRAMjet propulsion, where we were looking, the sponsor was a Hypersonic Transition Office, where they wanted to get validation quality data and fast turnaround CFD on realistic inlets. So these are high performance inlets, three-dimensional inlets. And as such, before this project was launched, there were far and few data sets that tells you what is the flow, what is the pressure evolution, what is the shock structure, very few data sets. And so one of the big things that had to happen was when we prototyped these inlets, we wanted to know exactly how precise they are manufactured. So we wanted to know the surface texture, which all goes to the computational models. And I wanted to acknowledge Professor Horn, if he's here, for giving us this really great 3D CT scan of this entire inlet, and as well as Professor Kota, who's here, for giving us a very good characterization of the surface texture. These things were helpful in generating the CFD models, and that was done by Professor Edwards. And this picture shows the comparison from the fast turnaround models he has, and you see a small insert here, that's our experimental. And you can see they seamlessly blend together, which is the way you want to have it if your CFD, if your computations and experiments agree with one another. That's how they will blend. So that launches into the core topic of this morning, which is fluid structure interactions in hypersonic flows. So these two pictures are kind of why we care about fluid structure interactions in our lab. And so this is our SCRAMjet inlet that we had at zero angle of attack. You see the very nice shock waves, etc. But once we flip the angle of attack to 3 degrees, it's very benign. The shock happens at a wrong place, and the material or the structure deforms in a manner that it starts interacting with the shock. And this was actually a video. Essentially, we broke the model. Okay, and this is kind of our local interest, but there is a global interest in FSI, and there has been a lot of programs starting from the days of X15 through X43, and even the more recent ones, where this fluid structure interactions has been like a nagging point, right? You know, so nobody knows when it becomes important. When should you consider it? When I say when, at what point in your flight trajectory should you consider it? Is it cruise? Is it climb? Is it during the terminal phase? Is it during the initial phase? Nobody knows. Then, let's say it becomes important, or it deems to become important. Then the question is, how well can we predict? The actual answer is not so well, especially at high marks, or high Mach numbers. And that is because I will demonstrate to you that even when you have the smallest amount of structural coupling, the governing physics kind of gets out of control very quickly. Okay, so that's what I will demonstrate to you. And so capturing at least the core of the underlying physics is something of important interest, because that will dictate some of the reduced models and other computational tools. And I have to admit that this project was started by A4SR, and my admission is that this kind of fell on my lap because I knew a professor who was the authority in this field, and he pulled me in, and that professor is Earl Dowell. So he really got me on board. So So that's how I got started. And as such, I'm not an expert in aeroelasticity at all, and there are many people who know way more aeroelasticity, way more vibration than I do, so please pardon my ignorance as such. So, okay, so this is some of the previous work before, let's say, 2021. So the important things are the fluid structure interactions couples multiple domains, meaning there is a structural dynamics, there is an aerodynamics, there is a shock wave, and if you take thermal, there is a thermal heat conduction. So there's like multiple domains that are constantly interfacing with one another, right? So we have to start somewhere. So the place people started is take canonical geometries, right? So we looked at fluid structure interactions when you have a shock wave that happens across a control surface, or you have a panel and you have a control surface, there is shock wave, essentially you have a shock wave, and that can excite some of the panel's oscillation, and we will see some of the examples. Or the more canonical one or more basic one is forget all the shock wave, just think about a turbulent boundary layer past a panel. How do the turbulent boundary layer excite the vibrations in the panel, and vice versa? And so once again, the measurements poses their own challenges, and we will see some of them. So in the past, the measurements were limited to panel deflection and line of sight measurements, which provided an overall picture of the dynamics that goes on. One of the important key measurement was the pressure measurement, and if you consider panels, they are about a millimeter or smaller in thickness, you cannot mount a Q-like transducer, right, or any transducer. So we had to develop our own methodologies to circumvent this problem, to overcome this problem. And then in academia, what we study is what is called thin panels. These panels are less than a millimeter thick. But in reality, most of the aircraft panels are much thicker than that. So the question is, why do we even look at that? And the answer to that is most flow environments are much more hot and caustic. So those thick panels undergo a lot of this thermal buckling, a lot of this nonlinear behavior, but we are not able to simulate the flight environment. So within the academic environment, we can simulate to capture some of the phenomena that happens. We go for thin panels. Okay, these are panels that are a millimeter in thickness or smaller. And so far, studies have looked at panels executing about a millimeter type vibrations where there is some coupling between, there is established coupling between a flow and a structure. So what we want to do is we want to look at panels. To begin with, I'll show you the progression. We start with panels that execute much smaller vibration amplitude, and we'll see why. And then we progressively amp up the amplitudes of vibration. So the way this project was laid out, we had three teams collaborating. So NC State is the lead. So we partner with Duke and Georgia Tech. And we also work a lot with other federal agencies, both to synthesize a lot of their data, so we unify our findings, as well as do some joint experimental campaign at different facilities so that it gives a lot of training to the students. So this is the general layout of how we are going to present it. We start with what I call the simplest of cases, which is a stiff panel which has a very weak flow structure coupling, right? And you have a turbulent boundary layer over the panel. And for all these works, the boundary layer was at Mach 2.5. Okay, stiff panel, Mach 2.5. Okay, this is probably the simplest one, and you'll see why. And then, once we understand what happens, we are going to, on this same panel, instead of the turbulent boundary layer, we'll have the turbulent boundary layer, but we will make a shock wave impinge on this turbulent boundary layer. Okay, so this is still a weak coupling between flow structure, but now we have an additional complexity, namely a shock-induced flow separation. And we will see what happens when you add this complexity. Then what we do is we go for a much stronger coupling where, once again, there's no shock wave, same Mach 2.5 flow, turbulent boundary layer, but it is with a much thinner panel, so it will execute larger scale vibrations, and you'll see what happens when you do that. So as I described, so there will be, we'll call these two with two nomenclatures. The one without shock wave is called no SBLI. We'll tell you what SBLI is. It's called shock boundary layer interaction, essentially a shock-induced flow separation. And then we'll be looking at the case with shock-induced flow separation. So and these are the boundary layers that were measured. The data from Mach 1.5 was provided by Professor Granlund, acknowledge his contribution. And so this is what we do. So we need data set or information from structural vibration perspective, structural dynamics perspective, fluid dynamics perspective, and off-body flow field status. Right. So to do that, we put a couple of piezoelectric materials that provides the strain. Then we do a 10 kilohertz pressure field imaging using what is called a pressure sensitive paint. Essentially, we do no longer mount transducers. We spray paint an organometallic component, and that fluoresces based on the pressure. And then that gives you surface pressure data. And then for off-body data, we get velocity. And we do all these simultaneously. And that is the big challenge. And we demonstrate that we are successful in that. So before we do that, we characterize the panel. We wanted to make sure we understand the panel as much as possible. So we collaborators from Duke, this is Oldavo, he visited us. So we did a joint experimental campaign where we did a roving hammer test to get all the different modes that the panel will execute under various conditions that are representative of the wind tunnel, which includes that you have the panel sitting on the bench, but there is no pre-stress. So then you add some pre-compression, then you add a pressure differential between the two sides of the panel. So this one corresponds to typically what happens in our facility. So we give a torsion, so we give a pre-compression, we match the torsion that we give in the wind tunnel to what we do in the bench top, and we also create a pressure differential, so we emulate at best, at most as we can, what will happen in our wind tunnel. So this is bench top, and you can see these are the different vibrational modes. These are the different mode shapes. So I'm sure you've come across these. So let's start with the first thing. So weakly coupled FSI with just a boundary layer, right? So this is the boundary layer, this is the panel, and you have a flow. So what we do is we make comparisons with, so we make some simultaneous analogous measurements also on a rigid surface, right? Instead of a panel, just replace it by a rigid plate. So when we have a rigid plate, there is no FSI whatsoever. And we measure the pressure, and we measure the pressure power spectra. Neglect these peaks that comes because of acquisition. But all I want to show you is this. This is the power spectra of the pressure fluctuations that the surface experiences. Okay, this is the wall pressure power spectra, and what you see is the incoming boundary layer, the pressure spectra, is broadband. There is no preferential frequency. Please neglect these spikes, right? It's broadband. Essentially, that's what pressure fluctuation is essentially like a forcing. So you force the surface based on pressure, you tap it. So what the flow does to the panel, it creates a broadband driving of the panel, right? So that's what the boundary layer, the incoming boundary layer, does to the panel. Okay, what does the panel does in return? The panel does not care about all the frequencies. It amplifies only those resonant modes, those elastic modes that I showed you. And these are the different elastic modes that we got from the benchtop test, and you can see they align pretty well with what we measured. So essentially, the panel puts out only the resonant modes, so it puts it back to the flow, right? Okay, so now let's see what the boundary layer does to it. Then we take the pressure fluctuations measured on the panel. So this is the pressure field, P prime, or pressure fluctuation by the boundary layer on the panel. So what you see is, even though the boundary layer is experiencing fluctuations in all the elastic modes, only one mode seems to show a largest amplification compared to the other mode, and this is going to be mode number 2. Why is this amplified? I don't know, but this is an observation. Okay, so this is what's happening. Okay, so remember this, that when you have an FSI on a weak FSI without any bells and whistles, just on a turbulent boundary layer, in this particular case, only one elastic mode shows up to be coupling with the flow. Okay, why do I say this? Because there are two things that we can take from the pressure fluctuation measurements before I go to the next slide. One, the pressure fluctuation tells us the mechanical loading. So P prime tells you the unsteady mechanical loading. And the pressure fluctuation, if you trace the origins, where it comes from, it's an integrated quantity. And it's heavily biased towards the near wall flow structures in a boundary layer. And on the separated flow, you will see there is a shear layer that develops on the separated flow, separation bubble. It's heavily biased towards the shear layer over the separation bubble. So when you measure pressure, you actually get two types of information. You can infer, you can directly tell what the mechanical loading is, and you can also infer what is happening, what is the state of the flow above the surface. Okay, why do I say this? Because now, when we go to the next step, wherein we put a shock wave, this is called an impinging shock wave. The shock wave impinges on the surface. So when you do this, there is a lot of complexity that comes with it. So this is LES simulation from Adams back in 2017. This is done on a rigid plate. There is no panel on this simulation. And this is I use this to show the basic configuration. So you have this incident shock from the shock generator. This is called the shock generator. And that separates the boundary layer. And you have what is called a separation shock. And you have what is called a reattachment shock. This is called the reflection shock. So the separation shock causes the boundary layer to separate. And this region is called, the red color region is called the separation bubble. Okay, and it's provided and it's characterized by a length scale L separation, length of separation. And what this bubble does, so this is another DNS simulation. So when I play this, you'll see this bubble grows. As the bubble grows, the shock, the separation shock, kind of pulsates along with the bubble. So the separation bubble grows and contracts, and it carries the separation shock along with it. Okay. Why does the separation bubble grows and contract? That is completely different talk. It takes a long time to explain. But for now, let's take it as granted that the separation bubble grows and contracts. It pulsates. As it pulsates, it drives the shock with it, right? So when it drives the shock with it, the shock wave, if you measure the pressure beneath the shock wave, this is the spectrum you get. And this is very typical. The shock oscillates between of the order 100 to several thousand hertz. Okay, why does this matter? It matters because when you looked at the elastic mode frequencies of the panel, we saw that there are several modes within this particular broad band. So what can lead to is there could be coupling between the elastic modes of the panel with the flow modes, with the overall modes. So that's what we're going to look into. So before I go there, I also want to tell you that just to describe the separation bubble, we can say the separation bubble is like a resonator. It is broadband. It gets driven by the turbulent boundary layer, and it also has inherent unsteadiness. It kind of pulsates just on its own, right? So think of the separation bubble as a resonator. You put in a frequency, it may or may not resonate. If the frequency is in the resonant band, it will amplify. If it is not, it's not going to amplify. why do you need this? Because we are going to use this idea very quickly. So what I'm going to use in this lecture, or I'm sorry, in this talk is what I call a black box model. I'm not really going to go into what is happening within each each boxes, but what I want to show you is that the boundary layer dynamics impacts the separation bubble motions. The separation bubble motion impacts the shock waves, shock motion, and the boundary layer dynamics can independently modify the separation shock motion. So this is like a very phenomenological way of handling this. And I said the things get out of control very quickly when you introduce another dimension, the structure dimension to it, and this is what happens. So now what we are dealt with, so I'm not even talking about the separation shock motion at this point. When you add panel deflection to it, and you have separation bubble, now you have upstream boundary layer. The panel deflection can independently modify and get modified by each of this. So separation dynamics can modify the panel dynamics. The panel dynamics can in turn modify the separation dynamics. And you can pretty much draw a line connection between any of these rectangles, and that is what you're left with. It gets very complicated. So what I want to do, hopefully, in the next few minutes, is to uncover some of these complications, and at least in a very broad sense, so that we get some idea on what's going on. And to do that, we take help from comparisons between the same shock wave, same flow impinging on a panel, and you replace the panel with a rigid plate. So there is no FSI in a rigid plate, and there is structural coupling in a panel. So this experiment, basically, because it's very, it has multiple physics involved in it, it takes a lot of thinking to come up with the correct way of doing this. So essentially, we had to choose where we want to place the shock. We want to choose where we want to place the piezos. We had only 2 piezos, and we actually are getting help from Professor Peters in integrating accelerometers in our system, so that's great. And we also need a lot of help with what kind of flow diagnostics we had to do, so because we had to get the most information. So this is what we got, and this is the first result. So what I'm demonstrating here is this is the first ever reported, and this is the only reported in literature, of a simultaneous velocity, pressure, and panel deflection measurement with, that characterizes an FSI. So what you see here is the V velocity that tells you the shock waves. Then you can simultaneously see how the pressure waves respond, and you can see how all these are coupling to the panel displacement. Okay, so we take data like these, and we start deconstructing the data and start synthesizing what's going on. And in a separate campaign, this thing is done at 10 hertz. We also do a 10 kilohertz surface pressure measurement, so you can get the dynamics pretty well. So I'm going to run through this rather quickly because of the depth of time. So first things first, we check the mean. So would a stiff panel undergoing very weak flow structure coupling, would it impact the mean flow structure at all? The answer turns out to be no. We compared the strict line visualization, which is a qualitative indicator of the skin friction. That shows pretty much identical within our experimental reason. We measured the unsteady pressures. We measured the mean pressures. Within our experimental reason, they all look identical. So then what we did was, okay, we put a lot more emphasis into looking into the dynamics, because we saw the mean properties are not changing a whole lot. So to get the dynamics, we look for the power spectra. Essentially, it's the Fourier transform squared. So what we do is we take a panel. So these are the panel boundaries. We take different representative regions within our domain of interest. These regions include the incoming boundary layer, the separation shock, which undergoes the low frequency pulsations, and the boundary layers that reattaches after the separation shock, just to see if the boundary layer before and after underwent any modification. So this is the measurement domain. So we averaged large regions so that we can get a an unbiased picture of the dynamics that's going on here. And this is what's going on. So when we look at the incoming boundary layer, right, you still see this one dominant peak, right? And these are 3 different runs and 4 different runs. And 3 of the 4 runs, you'll see the peak is happening at elastic mode 3. 1 run happens at elastic mode 2. I don't know why that happens like that. There is a run-to-run variability. But 3 out of 4 happens at 3. Then we measure the separation shock. And you can see elastic modes 3, 4, 5 appear quite well. And if you look for elastic mode 1, you really don't see it. Number 2, you don't see it. So that's another thing that's going on. So the shock wave seems to like to amplify mode 3 the most. If you also see this, the peak of the power spectrum is where the separation bubble resonates the most. And that is the frequency, the elastic mode closest to the peak of resonance gets amplified more, which is kind of understandable. And the other modes, 5 and 6, they are also in the vicinity of the peak of this resonator, broadband resonator, so you see it. Interestingly enough, while you did not see any frequencies in the higher order mode, you start seeing some higher order mode frequencies after the boundary layer gets reattached. And that is because your shock wave is now pumping more frequencies, and that's kind of getting carried through in the boundary layer. So what is also interesting is we saw this, and we also noted from the previous configuration without a shock wave that the resonant mode number 2 gets amplified the most. Whereas when you put a shock wave, the mode kind of switches. In fact, it switches to what gets amplified the most by the separation bubble. So the question is, the point is, now we have a few details to come up with first cut incomplete picture of what is going on. Once again, the nuances are, I'm not going to get to the exact mechanics of what's going on. At least we know in a very weakly coupled interaction coupling, the mean separation did not change a whole lot. The static deflection of panel was measured to be like 10% panel thickness, less than 3% boundary layer thickness. That did not change a whole lot. So the mean did not change anything. Dynamics, you'll see, we saw they did change. And the boundary layer dynamics, we don't know if the boundary layer is how much it's directly impacting the separation bubble. So what we saw so far is that the panel dynamics seeds the resonant modes into the separation bubble. We saw modes 3, 4, 5 getting magnified when you have this FSI. The question is, does the separation dynamics, does it create the panel dynamics, alter the dynamics of the panel? And we saw yes, and we'll see once again it is yes. And we also saw that the panel dynamics also impacts the boundary layer dynamics. So it seeds some of the modes into the boundary layer, right? So the second question is, can the separation bubble pulsation preferentially impact the panel dynamics? And the answer, if you look at this in the panel strain, this is the purple is without an SBLI, just a boundary layer. The black one is with the SBLI when you have the separation bubble. And this is another piezo. What I want you to notice is when you compare the purples and the blacks, let's focus on this. We notice that the mode number 3, 4, 5 gets amplified the most. And if you see here, you can see the increasing strength of mode 3, 4, 5 in relation to the overall fraction. You can see that in both upstream and downstream piezos. And you can also see that mode 2 and 1, which did not get amplified, you can see diminished contributions. So what the separated flow does, it alters the panel's vibrations. It kind of creates its own weightage to which modes get amplified on the panel. So very quickly, so this is what we noted so far. So even at this very, very weak coupling, we still get a lot of crosstalk between the panel oscillations, panel vibrations, and the separating flows. Okay. Then what we did was we went to the next step where we said, okay, we understood something about weak coupling stiff panels. Let's start looking into much stronger coupling. And once again, Professor Dowell had this aeroelastic model where he predicted the flutter regimes for our wind tunnel. So he pretty much came up with the panel design or panel dimensions and thickness, which he predicted if we place it in our wind tunnel, it is going to flutter. Okay, so we built it, so we put it in our wind tunnel, and what we will see is, so this is what happens when we are away from the boundary he specified. So this is pressure fluctuation mapped, okay? So imagine you get pressure over the entire panel and you subtract the mean. So this is what you get. You'll see, if you follow this, you'll see some red patches, that is positive pressure fluctuations kind of convecting over your field of view, and some blue patches, the negative fluctuations kind of convecting. You probably can map the structures yourself, you can see, eyeball it. But then, when you go into the regime where he says, where he predicted there's flutter, this is what happens. There is no more convection. First of all, the pressure fluctuation gets a lot stronger. And in fact, what you will see is, you'll see an alternating red and blue band appearing at any particular location. Yes?
How do you dial in that particular response? When do you change to go from your random fluctuations to this?
You change the delta P. Pressure variation, I mean pressure across the plate.
So your tunnel, you can't change that really. You change like the back pressure?
You change we have a dial to change the pressure underneath the panel.
Oh, okay. So you got pressure control.
Yeah, we can control the pressure. And what also happens is during the, so this is what is called the lock-in, or what we call, I don't know if it's a flutter, I'm not good with terminologies, but clearly, this is the corresponding, red is the piezo that tells you the strain rate. So you can see there are occasions when it's noisy, and there are occasions when it's like really good sinusoid. And when this good sinusoid happens, the corresponding pressure gets locked in. So this one is very different from very weak coupling. So once you strengthen the coupling, what you will see is your your mechanical loading or your aero loading, aero response begins to get locked in to your panel oscillations. Okay, and so a flutter, if you ask any expert, they will say it's a one-way street to damage. There is flutter and there is pretty much a damage. You pretty much cannot recover your structure, is what I keep hearing. But what we also see is that, so we have some issues, meaning during the run itself, you'll see the panel undergoing plastic deformation. And you'll know that because this flutter is not a continuous sinusoid. You'll see breakages. I mean, breakaways from flutter, and then it re-enters flutter, and then it breaks away from flutter. So there is a lot of interest in knowing why these breakaways and re-entries are happening into flutter. That comes into the domain of like mathematical modeling and like incorporating the physics. So this is kind of where we are in this FSI research, but this research also created a lot of derivative works and directions. The first one I want to talk about is controlling the FSI, right? So so essentially the point is that your aircraft will not have one panel, it will have multiple panels. So even if you have a weak coupling in the leading panel, as you keep marching towards the 100th panel, you'll have much stronger coupling. So there's always a desire to mitigate the fluid structure coupling. And the go-to way of doing it is creating dampeners. But the problem with dampeners is they take a lot of space. And also it's very hard to put a dampener on a panel that's clamped on all four sides. So what the question was, can we come with very small acreage, small footprint methods to stop the FSI from coupling to happening? So what we did was this. This is kind of accidental, have to admit. So what we did was we had two piezos. Piezos give voltage under strain, or you give a voltage to piezo, it creates a strain. So what we did was we gave a voltage to piezo such that it couples with the resonance of the panel at an elastic mode that is not picked up by the boundary layer. Okay, so the boundary layer picks up mode 2, elastic mode 2, based on our experiments. We said, let's excite mode 3, right? So our expectation was that when you excite at mode 3, you can see it's like 20 times larger. So we thought, okay, now we can take the panel away, the boundary layer response away from mode 2, and most likely we are going to get a strong response at mode 3 because we are 20 times higher in our forcing. But what we saw, much to our surprise, is that mode 3, where we are forcing so hard, never showed up, and the coupling that happened at mode 2 also tapped out. And the footprint of this, we could miniaturize this transducer, this piezo much more than what we had. The point is that this is one way of miniaturizing and decoupling the flow structure coupling. And this has a few applications that's over and beyond FSI coupling. A piezo, most of you know, the voltage that we sent in for this is 20 volts. And the piezo can easily take 200 volts and creates a much larger deformation. And this opens up avenues for morphing structures. And that is a big hot topic in hypersonics. How do you morph a structure so that it can traverse a whole range of Mach number without creating bad effects? That's one thing that came out of it. So the other thing is dynamically shaping structures. So here now, each piezo, when you cut into an elastic mode, it's in sinusoidal way. Can you cut into multiple modes so that you create a dynamically shape-changing surface? Once again, these are concepts that are coming up in the hypersonic world, and so those are the things that excite this community in the future. Pressing on the materials integration topic, the other thing that we are also interested, like you said, we are very much interested in propulsion. So what happens when you do a sub-design Mach operation is you create a large areas of flow separation. We saw that many times and in this talk. So what we wanted to do was, can we use this FSI and some derivative efforts to mitigate large-scale separation? When I say large, we are talking 10 times the boundary layer thickness, or of the order several inches, right? So the idea is that we want to explore the advances in the materials world, and we explored the use of what is called soft materials or polymeric materials. And what we wanted to do was we integrate those polymeric materials on one of the faces. So we put an implant of the material on this face, on the surface that is undergoing separation. And this is the separation picture. So this band here is this arc here is the separation, right? When you do not put any implant. Here is the bottom one is the same as this. Now if you put an implant, and I have to acknowledge Professor Kota for helping us with some of the implants. So when the bottom one, when you put some implants, when you put the implant, you can see the separation goes down noticeably. Depending on how you measure, it's at least 20%. The other interesting aspect of adding the implant is that you also spread out the pressure gradients. So pressure gradients is what creates the boundary layer separation to happen. Now, if you put soft materials, what it does is it spreads out the pressure gradients. Because it spreads out the pressure gradients, you get a much wider distribution of pressure, You also reduce the unsteady loading, you can see here, as well as you can see in the parse spectra comparison. You get multiple dividends by integrating new materials. Once again, this is a project that we just started off with, so there's a lot more aspects that we can look at, a lot more directions that we can go into to integrating new materials for positive gains. The other other project that was derived from this is, once again, in the realm of inlets where sub-design operation, you'll see a lot of, so this is operation at Mach number. You'll see like one shockwave sticking around here, but this is at Mach 2.5. This is an experimental image from inlet operating at 2.5, designed for 2.5. Now if you bring it down to 2, all of a sudden you see so many shockwaves. And what it causes is it causes a constriction of the flow. What we are hoping to get to is to create a smart material, integrate a smart material to one of the walls that can open up so that you can alleviate some of the constriction. The more, so the constriction is like you constrict the flow, you create more shocks. That constricts the flow further, you create much more shocks. So we want to use some of the advances in the smart material world to open up the flow so that you can mitigate the constriction. I'll be remiss if I don't mention some of the new hypersonic facility that is coming up. It's instrumented by Professor Srinath with the seed grant from College of Engineering. So the idea of this, the unique selling point of this facility is the very large runtime that this facility offers compared to many other facilities. We saw that these fluid structure interaction, when you add thermal component, it takes several seconds for you to see any impact of the interactions. Similarly with materials, you'll see a lot of material degradation happens only on a long time scales. So the long time scale wind tunnels are far and few in the US, and our facility will be the first and the only research grade facility in the Southeast USA, so I'm hoping that it will create a lot of traction and attract a lot of students. So that's about it. Thanks so much. Thanks for your interest.
I have a few questions.
Yeah, very interesting. My question to you is about the use of piezo strain, to generate that vibration you measure. And indeed, in the strain mode, you see that certain right? And you have the pressure, piezo pressure detection. It's not the same piezo, right?
Pressure is always pressure sensitive paint. We cannot put a transducer.
No, I'm saying you say you have a piezo strain PSD, right? You generate that, drive it, 20 volts, whatever you used to have a pulse generator, right? When you have the force vibration, where you measure that? It's the same?
On the other side. So this one is the underside of the panel. It's not exposed to the flow.
Yeah.
The other side of the panel that's exposed to the flow, we paint the pressure sensitive paint and we measure.
Yeah, I understand. You're driving and your detection not the same here, right?
Driving with this piezo, detecting with the other one.
Okay.
The graph is what we measure.
Gotcha. Right.
And we can also flip. We also flip it.
That kind of can explain why you have the force measurement is not great, because you generate that one with that pulse, and when they propagate to your pressure one, depending on what panel material you have, sometimes you don't get much propagate to that.
True. I agree with you. Yes.
How do you calibrate the PSP panel?
Okay, we calibrate PSP multiple ways. My students here, they are way more well-versed than I am. I'm just going to tell something. If I do some mistake, please let me know. Please correct me. So 2 or 3 ways. One, we have a vacuum chamber, or pressure controlled chamber. So we take a sample, put it in the chamber, calibrate at different pressures. So we get the 1 bar is our reference. So the reference ratio of the intensity to the reference intensity correlates inverse is linear with pressure. That's one way. Second way is to calibrate unsteady, like fast response pieces, fast response PSP. We also have a steady, much higher, signal generating paint that is commercial, and they give a calibration. So we use that also. Third, we have a Q-light on a rigid plate. So we have some legacy data set from a rigid plate. So we paint the piezo on a rigid plate and compare it with Q-light. So is that okay? Yeah.
So you can change the temperature inside the vacuum chamber?
We cannot change the temperature, but we have a vacuum oven now where we can change the temperature.
How big the vacuum chamber?
Anyone?
That's probably 16 inches by 12 by 12.
Okay, thank you.
So 16, 12, 12. Yes, Gian.
Yes, I have a question kind of following the Ashion's comment, but it's probably from a pretty different perspective. So I understand you're taking that pressure from your PSP and just assuming that your piezo is successfully pumping in perturbations to your flow. So I'm wondering, do you have any insight on you can sort of lower that pressure, fluctuation across the entire flow band? So where did the energy go?
So
Is it, in this case, the mean flow didn't change at all?
I think so. This shift happens. That's 30%. I think a good part of it is just it's just like a flow it's taken during the runtime. The mean pressure already changes. It comes down. So this 30% change, it's probably not all 30%. It's probably more like 5% at best. So it's not. It turns out the mean flow, the overall pressure par spectra, it's not changing a whole lot. It's changing by maybe 5% or reducing. Where is it going? I do not know. Yes, Sri.
I want to ask you a thermal question.
Oh my God.
So when you are calibrating, like Minta asked, in a vacuum chamber, of course you have a little bit more control conditions. But when you run this experiment, you have friction heating on the wall. So your temperature is actually different than
Yes.
what it is. So your PSP is
So we measure.
sensitivity to temperature is well known. So how do you account for that calibration?
For now, we do not account for it, and that is because over a 10-second run, the temperature reduces by about 5 Kelvin. So we know so we have literature of the response, and it turns out within 270 or 300 plus minus 5 Kelvin, the response does not change a whole lot.
What about if you got higher Mach numbers?
Of course, our highest is Mach 4.
Right now.
Right.
If you go to 6 or 7, you're
Right. So obviously we have to get the thermal component into the picture for sure. The thing though is, for you to realize the adiabatic temperature, it takes several tens of seconds to minutes. So my guess or my hope is that we are going to escape out of the temperature dependence because the runtime is still about 10 seconds.
So if you get longer, then you think that it will settle.
It will increase. We have to account for it. There's no two ways about it.
There's no change in potential body layer effects, nothing because of that.
There could be, I do not know, but the current limit on the pressure sensitive paint, the highest temperature where you can still get a dynamic response like this is about 100 centigrade. 100 centigrade is nothing in hypersonics, right? So so that's why we have to massage our experiments such that we live within the 100 centigrade. That being said, that 100 centigrade happened, like the expansion to 100 centigrade happened like in a paper that I reviewed 3 months back. It's that new. So we are partnering with AEDC Tullahoma to at least reproduce that so that we integrate into their facility and maybe even go a little further more.
So what you're saying is that if you have a temperature that's higher than 100 centigrade on the surface,
Yeah,
you can't take
no,
anything
you cannot get
about
it. No, not happening.
So it'd be tough for internal.
So in reality, when you're dealing with this kind of stuff, the friction heating on the surfaces is significant, right? I mean, that's what they, even like when you have electronics inside and all the stuff, they all need to be cooled. They don't know where to dump the heat.
Yes.
Because the external surface is getting really, really hot.
Yes.
So that is an issue with the surface anyway, right? When you go to realistic problems.
Yeah, so the measurement, this tool technique has a limitation on temperature. So at the bottom of it, it comes to the formulation. I'm sure there are people working in other groups where they come up with new formulations that are a lot more temperature resistant, but still offer.
Temperature sensitive.
Yeah, so we can either do which will be great. So if you do a temperature sensitive, you can actually get two pieces of information.
Yes, right.
But then the quality depends on the words of the two, right? That's how it is. But anyway, there is a lot of research happening on this domain.
All right.
Okay.
Let's,
more questions, please email me.
All right. Thank you, Venkat.
So you got first I think you just were definitely trying to find it.
I saw it. That would be nice. I saw it. You were waiting. I remember that comment. It stands out so much. It's also one of the no, this is actually my okay. And keep my name license.
So there are a couple of undergrads coming in and cool one. I'm working in 6 people. We do not really do that PSP. So there's any more like cool. Yeah, changing I can still more. So there'll be probably around 3:30. Okay. I'll be there in the machine. All day. So it's 3 PSPs a year.
This one's got, you can if you want.
Yeah, so I did a couple of, I mean, the one was the three different things that we wanted. The regular one, everything is not everything. There is, so one case is where I have this no seeding, and then the focus is downstream. There are 3 cases. So with no seeding, I'm still getting around 1.2 the ratio. I mean,
okay.
So I'm not sure.
So ratio of what and what?
So the ratio of, so we have N2, C2H4 in the jet and air into air and air. Jet. So currently I just get used to it. So take the division. Here the ratio, last time it was around 1.3. So no, last time the N2 ratio was